Hey everyone, Brandon from Row64 here. Today we're going to be talking about logistic regression. This is by far one of the most fundamental algorithms for classification in machine learning. And just in brief, classification algorithms in machine learning have the goal of predicting the category or class to which a new data point belongs. The data set that we're going to be using today is a car insurance data set, and our managerial problem for this data set is to predict whether someone will purchase car insurance based on some characteristic information of the individual whose decision we're trying to forecast. Some of the attributes of the data points, often called features in the world of machine learning, that we'll be using to predict buying behavior are whether the individual has a driver's license, which is here in column D, whether they've been previously insured, which is in column F, and a myriad of other features that we might believe will have an impact on the purchase behavior of individuals being advertised car insurance. Picking which features to use is a really interesting topic, but it's beyond the scope of this video, so we won't be discussing how those features are selected here. As an example, I've created a recipe that has preset features in order to illustrate how to interpret the results of a logistic regression model. To pull up the logistic regression recipe in Row64, we're first going to click on the recipes button over here, and then click over into machine learning, the machine learning folder. And once we have this open, we'll click on logistic regression prescription. You can click on either example or insert. Example will actually run the file for you, and insert will just give you the actual function to run a prescription. There's a series of steps that need to be done to run the file, so I recommend clicking example and following along with the video. Just to cover what prescription means, and we'll need to briefly talk about what other kinds of analytics there are out there other than prescription. The three main types of analytics are descriptive, predictive, and prescriptive, which is what we're working with today. Descriptive analytics is focused on summarizing past events and analyzing what has happened in the past. Predictive analytics is aimed at making predictions about future events or trends. And prescriptive analytics is focused on providing recommendations on the best course of action to take based on the outcomes of our models. I'm going to pull up the recipe for prescription again and give a rundown of what's happening inside. So the first sheet formula is load CSVs. We'll be pulling in the car insurance data set. And the next three formulas are all part of what's called feature engineering. This is, in short, how we prepare the data to be in the correct format so that the model can ingest it properly. These three. I'm planning on covering feature engineering in a future video, but as of right now, what we're going to be doing is essentially transforming the data that is in string format. So let me find some. I clicked over on the input tab, and these gender, vehicle are in string format, and we'll just be converting those into numeric format so that the model can ingest it properly. Now that all the preparatory steps have been covered, we can talk about the actual model. Logistic regression is used to predict on data sets where our predicted variable has two possible outcomes. Examples of this would be whether a certain individual will default on a loan, which is a yes or no, presence or absence of a disease, and countless other managerial settings where our interest is in predicting a binary outcome. As mentioned previously, we're going to be predicting whether an individual is going to be purchasing car insurance. This is in column J, I believe. Let me see. Response is in L, actually, so it's J in the output data, but L in the original data, as you can see here. We're looking at L. Actually, it will be in column J. This is the output data. This is what the data format will look like after the feature engineering has been done on the data. So as you can see, there's a change from female, male as two new columns, yes and no as two new columns, from gender and I believe vehicle damage, yes, that was another one. Vehicle age was transformed into a strictly numeric column, as you can see in the vehicle age column here. The first parameter of the sheet formula found here is going to be the variable that you want to see to set as the predicted variable. As you can see in this example, the first column is J, which is our response variable over here. And all of the following columns that are in the sheet formula, B, C through N, will be the columns that contain variables which are presumed to have an effect on the predicted variable. The script should run automatically when you click example, and the results will be printed in a window below the data frame. You can see those results down here if you pull it up. They're with the coefficients. The first thing that you'll want to look at before you start interpreting coefficients, which we'll get to shortly, is the accuracy number, which can be found here. Accuracy is the proportion of correctly classified data points. There aren't hard and fast rules on what an acceptable accuracy is, but generally above 90% is great, and somewhere in the 70s and 80s might be passable. Once you've determined that you have an accuracy score that you're okay with, you can move on to interpreting the model coefficients. The model coefficients essentially tell you what kind of effect the columns you chose as features have on the outcome of the predicted variable. Before we go to the coefficients, I need to briefly explain what odds are, since the coefficients of logistic regression are interpreted in terms of odds. Odds are defined as the probability of an event divided by the probability of that same event not occurring. So, as an example, if the probability of an event occurring is 0.6, which is 60% statistics, but we always express probabilities as values between 0 and 1. And the probability of that event not happening is 0.4, because the complement of 0.6 is 0.4 when we're looking at 1. We can calculate the odds by dividing 0.6 by 0.4, which is 1.5. Therefore, the odds of that event occurring are 1.5. With that out of the way, let's finally get to the coefficients. We're going to take a look at the column that is headed with the title odds coefs, because the coefs column is expressed in terms of log odds, which is much harder to intuitively understand. Let's take the variable of vehicle age as an example. Let's see that here. Odds. You can see that the odds coefficient of the vehicle age is 1.52, roughly, which means that with every increase in one standard unit of vehicle age, the odds of the individual purchasing car insurance becomes 1.52 times more likely. The reason that I specifically said standard units of vehicle age and not just vehicle age is because the model makes use of something called normalization. Normalization is basically a way of scaling the data so that its distribution follows a normal distribution or a bell curve. The way that this coefficient interpretation should affect the way that we view the managerial problem is that since we know people who have older cars are more likely to purchase car insurance, when advertising car insurance, if we have a limited budget, we should restrict our advertisements to users with older cars. And that is a short summary of logistic regression in Row64. I hope you guys enjoyed, and I'm looking forward to seeing you in the next video.